Okay, so I'm going to start by talking about the modulus function. The modulus of a real number x is the distance of x from 0. So for example, if we consider a number line going from -2 to 2, the distance of -2 from 0, the modulus of -2 is 2, the modulus of 2 is also 2, and the modulus of 0 itself is 0. So the modulus of a real number is written inside bars like this, and the modulus of any real number x is simply its distance from 0. So the modulus of a negative number is the sort of positive value, but it's the distance from 0. We know distances are non-negative. An alternative way of writing that is to say the modulus of x is equal to x when x is greater or equal than 0 and is equal to minus x when x is negative. And this is what's called a piecewise function, and that simply means that there are different cases depending on the value of x. The function takes different values depending on the two different cases, and we'll see more piecewise functions later. But now a natural thing to ask is, what does the graph of this function look like? So this definition is really helpful in helping us determine what the graph looks like. So if we have a set of axes here, we know when x is positive, the modulus of x is equal to x. So we know we're going to draw y equals x when x is positive, and when x is negative we need to draw minus x. So we get something like this. So this V-shaped curve is the graph of y equals the modulus of x. So we've drawn here the graph y equals the modulus of x. And something funny happens here. At 0 we get this sort of corner. And this is quite special because when we have a corner like this, the function, the modulus function, is not differentiable at this point. Its derivative at 0 does not exist. And it's wrong to say that the x-axis is a tangent at this point. To make that a little bit more precise, recall the definition of the derivative. F dashed of x was defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And let's use this definition to think a little bit about the derivative of the modulus function at 0. So let's let f of x be the modulus of x, and let's also let x be 0. So then we obtain f dashed of 0 is the limit as h goes to 0 of f of 0 plus h, that's f of h, minus f of 0 over h. And then, now what is f of h? That's the modulus of h. F of 0 is just 0. So we've got the limit as h goes to 0 of the modulus of h over h. Well, now let's look back at the graph. We want to work out what this limit is. Notice if h is negative, the modulus of h is minus h over h, which is minus 1, because we see the gradient of this is minus 1. But the gradient of this is 1, and when h is positive, the modulus of h is h. So it looks like it could be either 1 or minus 1, depending on whether h approaches 0 from the negative values from the left or from the positive values from the right. So whenever this happens, when the two-sided limits as we approach from both sides don't agree, we say this limit does not exist. So this limit here does not exist, and therefore the derivative at 0 does not exist. So the modulus function is not differentiable at x equals 0. Okay, but it is differentiable everywhere else. You can work out the derivative everywhere else. Okay, so we don't need to worry too much about differentiating the modulus function, but I thought it's very nice to show because it's one of the easiest examples of a function that's not everywhere differentiable. Okay, so now we're going to move on to the following example. So we have an example here. We want to sketch y equals the modulus of 4x plus 1, and then solve the equation the modulus of 4x plus 1 equals 5. So firstly, just sketching the graph. So there are a lot of different ways we could do this. Let's just first think about y equals 4x plus 1. So if we were to draw y equals 4x plus 1, it's going to cross the y-axis at 1 and the x-axis at -1/4. So the graph looks like this. And then we want to draw the modulus of that. So remember, the modulus of a positive number is that number. So whenever the graph gives a positive y value, the modulus of that y value is again just the same thing. So, so here above the x-axis, we still get the same line here. But when 4x plus 1 is negative, when y is negative in this graph, the modulus returns the positive value. So what we need to do is just reflect this negative bit above, and then this new graph in pink, this is the graph y equals the modulus of 4x plus 1. Because the modulus of a negative value is the corresponding positive value. Okay, so we've got this V shape. So the graph of a modulus function is always some sort of V shape, or sometimes upside down. So we've got this V shape, and notice that over here, remember the modulus of x is -x when x is negative. So this is part of the line y equals -4x plus 1 in brackets, or y equals -4x minus 1 on the left. On the right, it's part of y equals 4x plus 1, as we can see. So that might come in handy later, because now we need to solve the equation the modulus of 4x plus 1 equals 5. So we can think about this graphically. We can add to the graph the line y equals 5, maybe here in green. There's the line y equals 5, and we can see from the graph that we're expecting two solutions. We've got one solution here, and we've got another solution over here. There are two solutions. To find them, there are a couple of different ways we could do it. One way is to use these two equations of these lines. Part of the V shape is y equals 4x plus 1, the other part is y equals -4x minus 1. And we could set both of those equal to 5, so that's one way to do it. A different way is to observe that the only way the modulus of 4x plus 1 could be 5 is if 4x plus 1 is, 4x plus 1 is equal to 5, or 4x plus 1 is equal to -5, because the only numbers whose modulus is 5 are 5 and -5. And then we have these two equations to solve. They're both linear equations, so we obtain quite easily the solutions x equals 1 and x equals -3/2. So there are two possible solutions, which corresponds to what we see in the graph. So drawing a graph is a great way to help you solve equations or inequalities involving the modulus function, because it will confirm your intuition about how many solutions you should expect. Sometimes you won't find all of the solutions, or you'll find too many if you're not careful and don't draw a graph. So I recommend you always draw some sort of sketch to help you do this sort of question. Okay, and now we'll just move on to solving an inequality. So if we have a different example, this time we want to solve the modulus of 5x minus 1 is greater than 3x. And again, a graph is going to help us do this. So we could start by drawing the graph. So we have two different things we need to put in our graph. The line y equals 3x and the modulus graph y equals modulus of 5x minus 1. So if we first think about y equals 5x minus 1, this crosses the x-axis at 1/5 and the y-axis at minus 1. So it goes to 1/5 like this, and then, but this negative bit, because it's modulus, we reflect it back up. So that's the graph of the modulus of 5x minus 1. And the gradient of those lines are minus 5 and 5. So when I now draw y equals 3x, that should be less steep. So this is y equals 3x. So we're expecting there to be two solutions. And this is one of the times when having a graphical calculator is an advantage, because if you forget how to draw a graph like this, you can use your calculator to do that. Right, so now we have two solutions we need to find. So now it again comes in handy to remember what we said earlier about the two different lines. We can work out their equations. We know this line on the right of the V shape is part of y equals 5x minus 1, and on the left side that's part of y equals minus 5x plus 1. So in order to find the points of intersection, we need to solve 5x minus 1 equals 3x and minus 5x plus 1 equals 3x. Okay, so because this line on the left is y equals minus 5x plus 1. So again, those are just two linear equations, so we obtain x equals a half and x equals an eighth, I think. So is that right? Yes. Okay, so we found this solution here is an eighth and this is a half. So we're interested in when the modulus of 5x minus 1 is greater than 3x. So we're interested in when the modulus graph in pink is above the black line y equals 3x. So the solution is x is greater than a half or x is less than 1/8. And we can write that in set notation if we really want. It's the set of x in the real numbers such that x is greater than a half, union the set x in the real numbers such that x is less than 1/8. Or even nicer, you can also write it in interval notation. We have x belongs to minus infinity, comma, 1/8, union a half, comma, infinity. So either of these two are what you'd have to give if you write it in set notation. Okay, so now we're going to move on to the graphs of modulus functions, more complicated modulus functions. So if we have y is equal to the modulus of f of x, we need to think about how to draw the graph. So we've already seen how to do this for linear functions, if we have something like the modulus of 5x plus 1. But in general, what is it we need to do to draw the graph of this? And the answer is we need to reflect parts of the graph below the x-axis in the x-axis. We'll see an example in just a second. And if we want to draw y equals f of the modulus of x, we need to reflect the graph for x is greater or equal than 0 in the y-axis. So this is because if you want to work out f of the modulus of -7, for instance, the modulus of -7 is 7. So when x is -7, we'll get the same y value when x is 7 and when x is -7. So the graph is going to be a reflection of the positive part of the sort of bit to the right of the y-axis is reflected in the y-axis to give us the left half of the graph. So let's see some examples. So we want to sketch firstly the y equals the modulus of x squared minus 3x minus 10. So it might help us at first just to draw y equals x squared minus 3x minus 10, because we see immediately this factorizes as x minus 5 times x plus 2. So this crosses the axes at x equals -2 and x equals 5, like so. And we know this point here is -10. And so we need to follow the instructions we just wrote down. We need to reflect parts of the graph below the x-axis in the x-axis. So this part of the graph here, below the x-axis, we're just going to reflect in the x-axis. And the positive parts of the graph we leave alone. And then this funny shape we get here in pink is the graph we want. Okay, so that's the answer. And then if we want to draw instead y equals the modulus of x squared minus 3 times the modulus of x minus 10, we need to follow the second set of instructions. We're going to reflect the graph for x is greater or equal than 0 in the y-axis. So I'll draw the graph again, like this. The instruction was to reflect the graph for x is greater or equal than 0, which is this bit on the right. We're going to reflect that in the y-axis. And then it gives us this shape here, where this point here is -5. So we get this sort of shape, W sort of shape, with a sharp point here, and we would worry that the function isn't differentiable there. Indeed it isn't, and the same is true at those 2 points. So that's the answer to part B. And then part C says draw the graph y equals the modulus of sine x. Well, first let's just remind ourselves what the graph of sine x looks like. So it looks something like this, between -360 and 360. And again, we're going to follow the instruction to reflect everything below the x-axis in the x-axis. So that would give us these 4 equally sized bumps like this. So that's in pink, that's the graph y equals the modulus of sine x. And now we want to draw y equals sine of the modulus of x. How would we do that? Well, again, we take the positive part of the graph, which looks like this, and we reflect that in the y-axis. So we get something that looks like this, where this is -360 and this is -180 here. And that's the answer. We're now going to do one final example. We have this graph here. We don't know what sort of equation this graph has, but we're given several points on the graph. We're given where it crosses the coordinate axes and the local minimum and local maximum. And we're asked to sketch y equals the modulus of h of x and y equals h of the modulus of x, labeling the images of the points a, b, c, d, and e. So to first draw y equals the modulus of h of x, we're just going to reflect any parts of the graph that are below the x-axis in the x-axis. So when it's positive, it will be the same, but then parts of the graph below the x-axis are going to be reflected. So we get something like this. And then we just need to label the images of those 5 points. So we can see A, B, C, and E all stay in the same place. So this is A, this is still -7, 0. E is still 3, 0. C is still 0, 11. And B is still -5/2, 15. But then this point D now moves up. So the image of D, I'll call it D prime, becomes 6, 5. So this negative y coordinate becomes positive. And the asymptote is still in the same place. But obviously if the asymptote was somewhere else, if it were lower down, it would become a positive value. Okay, let's now draw y equals h of the modulus of x. So this time we're going to reflect the positive part of the graph. So that's this part here in the y-axis. So we're going to get, should be symmetric, it's not quite symmetric, but something like this. So the point C stays in the same place. The point D and E also, E stays in the same place, and D stays in the same place. But now A and B move. What was previously, well, A and B are no longer part of the graph. So instead, we'll just label this point here, it's -3, 0, and we'll label this minimum point here is -6, -5. So A and B don't really have images. I think the way the question was stated perhaps wasn't quite right, but we'll just label, maybe it would have been better to say label the points of intersection with the coordinate axes and the maxima and minima. So that finishes this example.